Okay, good evening, everybody.
Good evening, sir.
Good evening, sir.
Okay. All right. We will pick up from where we left left off last week, and we hope to finish this week. So we had actually started looking at efficiency when we realized that we needed some timeout. So we will pick up their efficiency of the DC machine. And I'm sure you all remember now um, the important things to consider when you're thinking about efficiency. And these would be, in general, the power input, the power output, and the losses. So when we're talking about efficiency, we're talking about power output over power input. Right. Now, in a DC machine, there are a couple more losses than what we are used to for the transformer. Now, in the transformer, we had copper losses and core losses. Now, added to those in the DC machine is not is but are friction and windage losses and brush contact loss. So where the brushes rub on the commutator, some losses take place there in terms of the sparking that you will see. Let me define windage. Note the word wind in it. So windage is the resistance that air offers to the rotation of the machine. So it is coming up against air, even though the air may be still around it, air is offering some resistance to the rotation. And that is called windage. And that is also coupled with friction that you would have at the bearings. So those are losses that needs to be considered also. Right. Now, some losses are fixed, are constant, and some are variable. Now, from what we did with the transformer, you know that the variable losses would be in the windings. So the copper losses are the variable losses, and those depend on the current. So the square of the current and the resistance of the windings. The fixed losses would include now the core loss and the friction and windage losses. All right. So those fixed losses are called constant losses, and in our textbooks, they are denoted by the letter C to indicate a constant value. In some other books, because friction and windage occurs because of rotation, they are called rotational losses. And in some of those books, they also include the core loss as part of the rotational loss. Right? Since it's constant, so therefore the total losses would be your variable losses plus the fixed losses. So the copper losses plus the constant, and the constant we say are the core losses and the friction and windage losses. So many times you'll be just given a value for the constant loss. But maybe on one or two occasions you might be required to determine what those are. But most times you are given the values for the constant losses. Okay. Any questions here?
No, sir.
Okay, good. All right, so if we look at a shunt generator, we can see that the copper losses are taking place in the field winding. There will be an I square loss. You have some losses also in the armature winding, another I square loss. So the copper loss is the total copper loss in the machine then would be IA square RA. That would take place in the armature winding, and IF square RF taking place in the field winding. But power can also be written. So IF square RF can also be written as V times IF, because that also is another way of writing power, V times I. So the total losses then would be the copper loss, as we said before, IA square RA plus IF square RF plus C. Since this is a generator, the output power would be the current. So this is DC machine now, right? So don't make the mistake of multiplying by a cos theta here for a DC machine. I've seen that from time to time. Rarely, but I've seen it. So your output power now will be V times I, and your input, which is a mechanical power input, is going to be determined by calculating your output losses, your output power plus the losses, your output power plus the losses. So your input is going to be found using this formula. So this is the electrical equivalent of the mechanical input power. All right, so if we were to write the efficiency, then it's going to be P out over P in. And we said that P out was V times I. And then P in was V times I plus the winding losses and the constant loss. All right, now this diagram here is a power flow diagram, and it indicates how the power actually flows through the generator. So input mechanical power comes in here on the left. You have your rotational losses going off, and you have your copper losses going off. So these arrows going up are indicating losses. And then, so power is flowing, some goes off here, others continue, the remainder continues here, then some goes off in the windings as heat, and then the remainder goes to the load. So this is a power flow diagram, how the power actually flows through the machine. All right. So the PD here is a developed power. So it's actually an electrical developed power because mechanical power comes in first, and then it is converted into electrical. So it's a developed power. Think about it as like a potential energy. And then you will have the actual energy. So being produced out here. So potential builds up, but then you have to remove some more losses, and then you get what you an active energy here now. All right, so as we know about generators, mechanical energy or mechanical power is converted to electrical power as the machine rotates. All right, so yeah, so this is saying what I just said a while ago. The PD is an electrical power developed, but it's not yet the output power, right? Because you're going to supply the losses, right? Plus the output. All right. Omega M here is the angular speed of the shaft or the armature in rads per second. And omega can be written as 2 pi n, where n is in revs per second. TD is a torque developed. So again, that is not the output torque eventually. It's just a developed kind of potential torque. And shaft torque is what is actually getting the machine to rotate in the first place. So the torque that is input into the shaft. All right. So here is an example to determine the efficiency of a shunt generator. All right, so the question says a 320 volt shunt generator supplies a load current of 80 amps. If the iron friction and windage losses amount to 1.5 kilowatt, the shunt field resistance is 40 ohm, and the armature resistance is 0.2 ohm. Determine the overall efficiency of the generator. All right, so when it's a 320 volt shunt generator, it means that the output voltage, since the generator, the output voltage will be 320, and it is supplying a load current of 80, so I here would be 80. Iron friction and windage losses amount to 1.5 kilowatts. So we know that C, the constant loss, is 1.5 kilowatts. So as usual, we write down our data, what we know. So we can calculate our output power. Since it's efficiency we want, we know that the formula is going to be a P out over P in. So right away, we can calculate our output power from the data that we have. So P out is equal to V times I, and that's 320 times 80, and that's equal to 25,600 watts. All right, so we need to calculate the losses. Since we can't calculate the mechanical input directly, we need to find out what the losses are and then use that to find what the input power is. All right, so we can find the current in the field winding. Voltage across RF would be this voltage here, V, since it's a shunt motor, shunt generator, sorry. So a shunt machine. So the voltage here would be the voltage here, will be the voltage here. All right, so IF is equal to V over RF, and that works out to be 8 amps. Now, IA from Kirchhoff current law is, yes.
What is iron? What is the iron? Iron loss.
The core. The core.
Oh, okay.
All right. So just as in the transformer, the core loss is also called the iron loss. Because it's actually taking place now in the magnetic material, which is a ferromagnetic material, so hence iron. All right. From Kirchhoff's law, IA would be equal to IF plus I. We know what I is equal to already, 80. And we had worked out IF a while ago. So IA would be 88 amps. So the total losses then now would be using this formula. IA square RA, IA is 88, RA is 0.2, IF is 8, and RF is 40, so 8 squared times 40. And then the constant is 1500. So the total losses is 5608.8. So we can work out what the input is now. And it is basically P out plus P losses. So the input power is 31,208.8. And then from the formula for efficiency, P out over P in, we get an efficiency of 82.03%. So very simple, very straightforward here. Any questions on this?
No, sir.
Okay, good. All right, so here's another one. All right, so it says that a 150 volt DC generator supplies a current of 25 amps when running at 1200 revs per minute. Now, if the torque on the shaft driving the generator is 35.8 Newton meters, we should determine the efficiency of the generator and the power loss in the generator. All right, so the voltage given here would be the output voltage, and the supplied current would be a load current, so that would be I, the output current. So we can work out what the output power is using these two. We're given the input parameters, the shaft torque, and the speed at which it was turning. So we can actually work out power in, the mechanical power in, directly this time. So omega, remember power in is Ts omega m. So omega m is equal to 2 pi n. And small n here would be capital N divided by 60, as we found a week or so ago. Then the angular speed works out to be 40 pi or 125.66 rads per second. So P out is that 150 times 25, 3,750 watts. And P in is Ts omega m. So that's a 35.8 times 125.66. And that works out to be almost 4,500. And hence the efficiency is that output 3750 over 4498.76, 83.36%. All right. Losses can be found from this. We know that P in is equal to P out plus losses. So therefore, P losses would be P in minus P out. And that would be 748.76 watts. All right, so again, fairly straightforward. Once you start to get a hang of the data and what they represent, you should be able to go through fairly smoothly. All right, so this is what we had wanted to complete last week. We have done that. So we're now gonna go into part 3. All right, any questions? No? All right. All right, so today we'll be looking more at the motors, DC motors. And again, it's power flow diagram, different types, shunt, series, compound. And we look at different things related to each of them. So, and these are listed here. Later on in the evening, we'll get to efficiency. And again, you'll see some more work examples. So again, we kind of start out similar to what we had done last week. So by definition, motors convert electrical energy into mechanical energy and electrical power to mechanical power. All right, so recall that the same machine can be used for both a generator or as a motor. All right, just how we get the power in and out. All right, so now this is the power flow diagram of the DC motor. So input now is electrical. You have your losses in the winding, the copper losses. You have a mechanic, so electrical power is going to be converted to mechanical. So you have a mechanical power developed here. And then that mechanical power that developed isn't available out yet as mechanical power until it overcomes friction and windage, the rotational losses. And then after it does that, then the machine will rotate and you'll give you mechanical power output. All right, so P in then is electrical, and as before, copper loss, rotational loss. So the same definitions as we had before. All of the definitions that we had before. Now TS this time now is an output torque. The output or the shaft torque. So the shaft will exert some torque to move a load, get it rotated. All right, again, the machines, the type depend on how the windings are connected, the field windings and the armature windings. And if you have viewed the video of the DC shunt motor, you would have seen Mr. Campbell connecting the field windings to the armature winding in shunt, right, or in parallel. So that is one type of connection. Another type would be to connect the windings in series. And then the other type now is to have a series parallel kind of combination, form a compound machine, a compound motor in this case. All right, so we will look more at the circuit diagrams to kind of analyze what we're doing now. So this is the circuit diagram for the shunt motor. That the final lab 6 was about. So again, field windings connected in parallel to the armature winding. And this time, the voltage that will be given would be a input supply voltage. And it drives a current through the machine. And as load increases on the machine, that current will also increase. So the input current supplied to the motor is I. Part of that goes to supply the field winding, which will produce the field flux, right? Which is necessary to create this induced EMF as the machine rotates. All right. So remember, as current flows in this one too, you have the interaction, you have flux being produced here in the armature. And how you get the rotation now is the interaction of the two flux, the field flux and the armature flux. You can call them that. And then you have rotation as we showed last week. And as the machine rotates, you have the induced EMF as it cuts the field flux. You have an induced EMF. In the motor, although it's a generated EMF here, in the motor it's called the back EMF or the counter EMF. Because it tends to want to send a current this way, which would be opposing the current that is coming from the supply. So hence counter or back EMF. All right, the equation for the motor. So V, this voltage drop across here, would be the same voltage drop across here, would be the same voltage drop across here. All right. So that V is equal to the back EMF plus the voltage drop across the armature windings. So therefore, I can find what E is, right? By making it the subject of the formula here. All right, so this these two sentences are basically saying what I said just a while ago. V is equal to IF times RF. E is equal to K, I remember K was a constant that had to do with some of the machine parameters. K, phi, n. So phi and n were variable, but K was some constant parameters of the machine, like the number of conductors, number of parallel paths, that kind of thing. All right. I, as you can see, I would be equal to IF plus IA. All right. So we can work out what IA is equal to, because normally you're probably given the input current, and you can work out the field current based on the data given. So after you have those two, you can also work out what IA is equal to. All right. So a little bit of manipulation here now to work out what the power relationships are in the machine. So the voltage V across the armature is E plus IARA. All right, so if we should multiply that power input into the armature by IA, by the armature current, then would have V times IA, so input power into the armature would be equal to E times IA. So this is where we're multiplying by IA, right? And IA square RA. Now IA square RA would be the power loss in the armature winding. E times IA would be the power developed. So that's the mechanical power developed. Right? So it's equivalent to that. So mechanical power developed is equal to the torque developed times the speed of the machine. So I can work out what the developed torque is by this relationship. Right? So remember, torque is a rotational or turning force. All right, so we want to know what is happening to get the machine turning, right? All right. So we're gonna do some manipulations here. So we're looking at this equation, TD is equal to E times IA over omega M. But I want you to remember now that E from what we did last week was 2P for phi N Z over C, and omega was 2 pi, is 2 pi N, where N is in revs per second. All right, so if I substitute those relationships, I end up with something fairly simple. Torque developed is equal to some constant time the flux times the armature current. All right. So again, the constant is a constant for the machine, different from the other constant that we had for the induced EMF, but nevertheless a constant, just the same. All right. So the torque developed is proportional to the flux and to the armature current. All right. So separating them, torque developed proportional to flux, torque developed proportional to IA. But you may be able to tell me something about what the flux is proportional to. What else the flux is proportional to? Anybody?
The current, sir.
Which current?
The current that is producing it.
All right. And right. So the current that is producing it. So all right. So remember both two currents are producing flux in a sense. But we're talking about the useful flux here. So it would be the flux produced by the field winding, right? So the flux produced by the field current. All right. Now for a particular machine, since phi and Ia are variable, we can have different torques at different flux and different armature current. So I can write a relationship to account for that. So the torque developed at phi 1 and Ia 1 divided by the torque developed at phi 2 and Ia 2 gives me this relationship. And hence I can use that now to find maybe a new torque at new flux and new current. All right, but I wanted to point out that since the flux is proportional to the field current is usually a constant. Once the supply voltage don't change, the field winding resistance really is a constant also. So IF would be a constant. And if IF is a constant, then it means that the flux is a constant. So for the shunt motor, normally the flux is a constant. Now in the lab, you saw where Mr. Campbell was varying the flux in the field winding. And he had actually connected a variable resistor in the circuit and was varying the flux. So in that experiment, we were actually seeing a variation of the field current and hence a variation of the flux. And that did have some impact on the machine's operation. All right, so generally though, since the flux would be constant, since the field winding, field current is constant, then I can write the torque developed in terms of another constant. So all of these constants are different, right? So K times phi would be another K, right? In some textbooks, they have different subscripts for the constant, but I usually find it confusing. And I remember in KV and then KT and KI and all of those. So I just call it K and done. Because practically we are not going to be required to find out what that constant is for this module. All right, so torque developed is equal to K times IA. And you can see now that this is a linear graph, right? So characteristic also mean a graph for the particular machine. So the characteristics mean that anytime you see a shunt motor, you kind of expect this kind of graph between the torque versus armature current. So for the shunt motor, you have this linear relationship. Right? So the torque developed can be written in terms of the armature current. So at one value of the torque developed, you have a particular armature current, and at another value of the torque developed, you have another value of the armature current. So you can work out what the new torque developed would be if you change the armature current. And changing the armature current means changing the loading on the machine. All right, so here's another characteristic. This one is looking at speed versus the armature current. And we start out by looking at the induced EMF. Remembering that it has two equations, V minus IARA, and also equal to K phi n. So if I make put K phi n here to make these two equal, then I can get a relationship for n. And so n would be equal to V minus IARA over K phi. And IA is also equal to that. All right, so some verbiage here. As this is a shunt motor, the input voltage, the flux, IF and RA are constant. And as the load, the mechanical load increases, IA would then increase. Right? As the mechanical load increases, I increases, and then since IF is fairly constant, IA would also increase. But as IA is increasing, you can see that the numerator here now is decreasing. So as the numerator decreases, we can see that the motor speed will also decrease. So we see that gradual decrease in the graph as armature current increases. Now, for a well-regulated machine, the speed change from no load to full load is 10%. Right? All right. So I'm talking about commercial machines. What we have in the lab, you will find a wider variation, and it's because it's for experimental purpose. So it wasn't designed necessarily for efficiency, but more to demonstrate experimentally what's happening with the machine. Plus, we probably load it more than it is rated, than rated load in some cases. All right, so here's another one. So we want to show you before was speed versus armature current. But remember, armature current and torque are proportional to each other. So you will practically see the same kind of relationship there. So this goes through the derivation again. So as the torque, the developed torque increases. And the developed torque will increase when the shaft torque increases. So remember the power flow diagram when you're thinking about this stuff. So this T here is the developed torque. It's not the shaft torque. But as shaft torque increases, the developed torque also increases. So as the load increases, the machine will be required to generate more power to supply the load demand. Right, so that shaft torque will increase, the developed torque will also increase, input power will increase. So keep the power flow diagram in mind when you're looking at these, when you're thinking about the machine. All right. So similar to the speed versus armature current. The graph for speed versus torque is practically the same in terms of shape. All right, so here is another work example. All right, so let us look at this. A 200 volt DC shunt motor has an armature resistance of 0.4 ohm, and a certain load has an armature current of 30 amps and runs at 1350 revs per minute. So if the load on the shaft of the motor is increased so that the armature current increases to 45 amps, determine A, the speed of the motor, B, the torque developed, assuming, of course, that the flux is constant, because IF will be constant, right? All right, so let us look for present load, 30 amps, present speed, 1350 RPM. So we can work out what the induced EMF or the back EMF here is. E would be equal to V minus IA1 RA. And V is 200, that input voltage now. So 200 minus 30 amps times the 0.4 for the resistance, armature resistance. So we get 188 volts. So back EMF here is 188 volts. And N1, the speed that, so we're going to call our values that we're working with. In the first case, ones. So N1 would be the original speed in revs divided by 60. So that's 22 point revs per minute first, divided by 60 give you revs per second. All right, so I can look at the power developed now. They wanted us to find the speed. So we find the speed and the torque developed. So we need now to find the torque developed. All right. We need to find those when the current has increased to 45 amps. So what we need to do is to find out what they are under the existing condition first before the current is increased. So at 30 amps, the speed is 22.5 revs, and we're going to work out what the torque is at that current before we look at what it will be at 45. All right, so the power developed, E times IA would be also equal to torque developed times the angular velocity. And omega m is 2 pi n. So we can write, work out what that torque developed is in terms of E times IA. So E1 times IA1. So E1 was 188. IA1 is 30. So the power developed is that. And the power developed written now in terms of the torque and angular speed is 2 pi n1 times TD1. So therefore the torque developed at 30 amps would be this TD1 over 2 pi n1. So that's 39.9 Newton meters. All right, so what we need to, so we know what the speed is at 30, and we know what the torque developed is at 30 amps. So the question now is to find out what the speed will be and the torque will be when IA increases to 45 amps. So, all right, I want you to do that. Based on what we have done so far, change the armature current, call it IA2. IA2 would be equal to 45 amps. And work out what E2 is and what TD2 is for me. So I'm going to give you 10 minutes to do that. Okay?
Yes, sir.
All right, good.
Sir.
Yes, sir.
So about when they will get back in mid semester them, sir, everybody.
Uh, only God can tell you that, you know. I'm doing my best. But you
So
know, you're
which
gonna have one next week too.
our
That
next test.
yeah, that one you I'm sure you'll get back quicker, much quicker.
Okay, so but through me the year they say like depends on the grades them from this test so that determine if we get another test.
No man, we actually I think last week, I don't know if you were in class last week.
No, I weren't here last week, sir.
Oh, right. Last week there's one more week for classes. That's next week Tuesday.
Yes, sir.
And we should finish today. So we will have that time next week to do
The other test.
another test. One that you can do online, really online this time, not me sending you something and you do it and then try to upload it.
Or it's like multiple choice or something like that.
Yeah, yeah. So you should be able to get back the results within hours.
Okay, okay, okay. Okay. And then the lab that I see you sent, it's due Thursday, and then that's it for labs. Are we gonna do the other one, the fifth one?
I actually posted two more. Um, one of them I normally use as an assignment. The one with the shunt motor.
Yeah, yeah, we see that one. Yeah, we see.
Right. So that one is there plus the transformer one
So the
also.
transformer one is for Thursday.
Well, there are two transformers. The one for the polarity is for Thursday. Transformer polarity.
Yes, sir.
And then there's also the transformer open circuit and short circuit test. I may not collect that one and just let you do the assignment.
The assignment. But
Right.
still do the other one though.
Yeah, it will be good for practice. I mean, if you want to do it and submit it, I will mark it. Um, God give me strength.
All right, sir. All right, sir. So somebody just send a message. So when is the finals?
I think the university will set those dates, and I'm not sure yet. I don't know myself yet. But I know starting next week, Wednesday is study week. So I'm not sure exactly when the dates. So 1 week of study week, and then after that, I think will be the final period.
Yeah, so normally go after that exam week. Well, exam period, yeah.
So I don't know the date yet.
All right, sir.
All right. Topics for upcoming tests. I really haven't decided yet. But I think we had covered units 1 and 2 in the first test. So maybe 3, 4, and 5. Yeah, I think we had done units 1, 2, and 3. So maybe 4 and 5 mainly, and maybe some very simple things from 1 and 2. Anybody finish? All right, so how we getting on?
Yeah, when you think we finish, but to look at make an error, so I'll go again, sir.
Okay. All right. You alone working, I guess?
Sir, I haven't got it as yet, sir.
All right. So at 45 amps, what's the new induced EMF? Or be E2?
So I get 182 for that.
182.
I think I got 182 volts.
All right. Yeah, that sounds right. All right. So then you now need to work out what the torque develop is.
So I would find the
So
power first.
right. All right. So what's the power you have?
5,460, sir.
Actually, I get 8,190. 8,190.
8,190. All right. All right. Let's look. All right. How I'd approach it was to find a new speed. So after I found the E2, well, let's see if we can find the 8,000. 8,190, right? Good. Right. So that was, yeah, that is correct. 8,190. All right. So I had used the relationship now between the two values for the induced EMF. Using this relationship or these relationships. E2 will be K phi 2 N2 and E1 will be K phi 1 N1. But we were told that the flux remains constant, so phi 2 would be equal to phi 1. Hence, phi 2 and phi 1 gonna cancel. The k's will cancel. So we're left with N2 over N1. So I can work out what N2 is from using these E2 over E1 equal N2 over N1. So N2 then would be equal to 21.78 revs per second. All right. So having that speed, I can work out what the torque develop is. So I need to find the torque develop. IA2 is 45, N2 is 21.78. Everybody with me right here?
Yes, sir.
Okay. Let me see what's in the chat here. Okay. All right. Good. Good. All right. So using the 8190 that you had found and relating it to 2 pi n2 TD2, I can find TD2 from that. That works out to be 59.85. Or I could have used the torque and current relationship, since for the shunt motor, the torque is proportional to the armature current also. So TD2 over TD1 equal to IA2 over IA1. So TD2 equal to TD1 times IA2 over IA1. So I could have found it that way also. So all right, so this one involved a little bit more working out, but not very, very difficult, right? By the way, the bird gives a lot of practice with these kind of problems. So you should practice them. Spend an hour one evening, and you'll probably do maybe 10 of them in no time, but you'll get a quick feel of these problems. Mm-hmm. All right, so everybody okay with this?
Yes, sir.
All right, good, good. Come on. All right, so we're gonna go on now to the series motor. And in this case, the windings are again connected in series. So the same current now will be flowing through both windings. So V here now is going to be equal to the voltage drop across the two windings plus the induced EMF. All right, so that is written like this: V is equal to E plus I into RA plus RF. Then I can work out make the induced EMF the subject of the formula. So E equal to V minus IA RA. IA into RA plus RF. And again, E is equal to K phi N. Now, when there's no load, no current will be flowing through here. So there won't be any rotation. Right? So no current, but you actually have some kind of residual induced EMF, right, at no load. So I is equal to 0, but E is equal to V minus all of that. All of this here becomes 0, so E is still equal to V at no load. And that is due to a residual flux in the machine from previous operation. Now on load, I would be equal to IA and it would also be equal to IF. And remember that torque was proportional to IA, so it's going to be proportional to I. And since the flux is also proportional to I, then the torque developed is going to be proportional to I squared. So I times I, torque is proportional to I squared. All right, so it showed this relationship for the early part. So torque is proportional to I squared. But as I increases, the machine becomes saturated. So the flux won't change as I increases because the machine becomes saturated. So then torque just gonna be proportional just to current. So not to current square, but as the machine becomes more saturated, torque is proportional to the current. Because phi now going to become constant as the machine saturates. So this becomes a constant. So torque is not, again, going to be proportional just to IA, which is I. All right. So it requires a little bit of analysis, just a bit of insight when you're looking at these things to understand what's happening. But once you do your reading and your practice, you'll be on top of things. All right, so the first graph we show was torque versus current. This one now is speed versus current. And how we arrive at this graph now is again detailed on the left here. So as the machine is on load, you have a value for the current I. And we again equate the two equations for induced EMF, K phi N equal to V minus IA into RA plus RF. So I can end the subject of the formula. And then as you can see that as I increases, the numerator decreases, right? But here the denominator is increasing also. So as I increases, the denominator increases and the numerator decreases. So the net effect is that you have a decrease in the speed as I increases. So N is inversely proportional to I. Right? So at low current, the speed is extremely high though. Right? And so there is a condition that you should not operate the series motor unloaded because very high speed can develop, at low load. All right, so a series motor would normally be coupled to its load to prevent the no load operation or that speed runaway. All right, so a similar relationship for the speed and the torque. So you can read through this. Again, yes, you can see that kind of inverse relationship. As torque increases, the speed decreases. All right. Here are some things on the compound motors. I wouldn't really, well, you can read them up. I don't think I had any questions on those, but you can read it for information on the compound motors. All right. And how the machines, the different machines are applied in practice. So there's a slide for that here. So something that you can read up, to have an idea as to how they are utilized. And let's get back to efficiency now. So the efficiency of DC motors, and again, once we're talking about efficiency, we start to think about power flow. All right, so hence my power flow diagram is reproduced here. And efficiency again, P out over P in. P in is electrical, P out is mechanical. P in is equal to V times I. P out will be equal to TS, the shaft torque, times the speed of the rotor, the shaft. All right, so in this case, since it's a mechanical output, we usually have to try to find it from the electrical parameters, electrical input, and the losses in the machine. So you will see that we're gonna be using some of the same parameters, armature winding loss, field winding loss, and the constant losses, but the equations are gonna be different now. All right, so P out is equal to P in minus losses, and those are the losses. So it's P in minus, in brackets now, IA square RA plus IF square RF plus C. Right? So you probably notice that almost kind of inversion. So efficiency then, P out over P in, VI minus that, so all of the P out up top here over VI. All right, and similar for the series motor. It's just that you're gonna have one I now, because IA would be equal to IF would be equal to I coming in from the machine, from the supply. So the copper losses would be I times RA, I square times RA plus I square RF. And then you have the constant losses. So P out is equal to VI minus all of that. All right, so it's just basically when you see all these letters, you might get a little bit, you might feel a little apprehensive. But once you start to put in numbers, it works out fairly easy. All right, so bear in mind that as quick as you can, you convert these to numbers, and then it will work out. You will see how simple it is. All right, so here is another one, another example. This time it is a series motor, efficiency of a series motor. All right, so a 250-volt series motor draws a current of 40 amps. And the armature resistance is 0.15 ohm, and the field winding resistance is 0.05 ohm. Oh, you know, I never noticed that A before. Determine the maximum efficiency of the motor. Anybody remember the conditions for maximum efficiency?
The fixed and variable losses are equal.
Right. Very good. All right. So again, as usual, we write down in the data from the problem. Write down what we know, so we can calculate P in from the information given, V times I. So that's 10,000 watts. Losses, since it's a series machine, it's the same current through all the both windings. So losses I square RA plus I square RF plus C. So maximum efficiency occurs when variable losses equal fixed losses. So that is when PCU is equal to the constant losses. All right. So PCU is I squared into RA plus RF. And that works out to be 40 square into this. So that's 320 watts. So therefore, the total losses done would be 320 times 2 for maximum efficiency. PC plus C, 640. Now, P out would be equal to P in minus losses. So that's 10,000 minus 640. So it's 9,360. And efficiency then is P out over P in. And that is 93.6%. All right. Any questions on this? All right, so this one just calls on you to remember conditions for maximum efficiency. Otherwise, everything else is basically straightforward. All righty. And then here's another work example. So this time, this one says a 250-volt series wound motor is running at 500 revs per minute, and its shaft torque is 130 Newton meters. If the efficiency at this load is 88%, find the current taken from the supply. All right, so series motor, so V in, the input voltage will be 250. The current, we don't know yet. That's what they want us to find. Shaft torque, 130 Newton meters. Speed of the machine, revs per minute, 500. So we can convert that to revs per second since we want the output power. All right, so omega m would be 2 pi n. So So 2 pi divided times capital N divided by 60. So 2 pi times 500 over 60. So 52.36 rads per second. All right. So P in V times I. V is 250, so 250 I. And P out is Ts omega M. So that's 130 times the 52.36. That's 6,806.8 watts. And therefore, efficiency was given at 0.88, 88%, 0.88. So it's P out over 250I. So therefore, we can work out what I is. And I works out to be 30.94 amps. All right, any question on this? All right, so I guess we're good. All right, so I'll give you a little activity to do. There's something called armature reaction. And it occurs when the machine is carrying basically a large armature current. So I want you to read up on it and see what kind of effect it has on the motor and on the generator. All right. So it will affect some of the equations that we know for the machines. So that's what I mean by support your description of the effects mathematically. So some of the equations are going to be affected when you have armature reaction. So you just read up on that. Both the Bird, well, all the books will tell you about it. Bird is probably more simple in terms of its explanation. Use maybe a little bit more detail. So yeah, read up on them and find out what is armature reaction and how it affects the machine. All right, and there are some practice exercises. So I think this is where we probably finish for the, yeah. Somebody's preaching to us over here. All right, so you may notice this last slide here. Last year when at the heights of the coronavirus, I kind of found ways of trying to help the students to get their minds off all of the stress that came at that time with lockdown and no face-to-face classes and things like that. So I had prepared some things for each presentation for them to do. So this, but I took them back out this year because I suppose probably persons were more used to what this new normal. But this one I'm leaving still because it's something that you can think about at all times. So it's there, you can read it. Whatever is true, whatever is noble, whatever is right, whatever is pure, whatever is lovely, whatever is admirable, anything is excellent or praiseworthy, think about such things. All right, so think about good, uplifting things, and don't get your mind down with all of the stresses that life can throw at you. All right.
Okay.
All right. So next week we meet for the test at the special request of Mr. Atkinson.
All right.
All right.
So next week test, would it be like second test? I would be like a makeup test, if I may say.
Let's say
Addition.
all right. Let's say an addition right now. I wouldn't want to call it makeup, but maybe it's the best of two.
Okay.
All right. So maybe it's the best of two. Yeah, as you would have realized, I'm still struggling to mark because marking and preparing is really, really time consuming. So we're struggling. And not only
So
me,
what
I
about,
understand other lecturers are doing this, are struggling also.
so you mentioned the topics earlier?
Yeah,
Unit.
unit 4 and 5 for sure. And maybe a couple things from the other units. But unit 4 and 5 for sure.
Other units, you mean? Oh, okay.
That
Previous
would be-
units, sir, the previous units?
Right. I mean, I have to find enough questions for you to do for multiple choice. All right, but for sure, units 4 and 5. You wouldn't get anything out of the other units that you wouldn't have known before. All right. So in short, come prepared. All right. Because think of it this way, it will help you to prepare also for the finals.
Okay, sir.
To in a better position for the finals.
Makes sense.
All right. All right. So all the best to everybody. I'll see you next week.
Thank you, sir.
All right, sir. Thank you.
Okay, sir.
All right.